Hello, and welcome to our Sustainable Recycled Water Recharge Program presentation. Our Capstone project sponsor is the Metropolitan Water District of Southern California. Our faculty sponsor and advisor, Dr. Sonia Lopez. Our teaching assistant, Isabel Escobar Sanchez. This is our project team. It consists of a group of senior design students that were intrigued by the challenge of working on a water resource project that had far-reaching impacts on both the community and the environment. Our team consisted of 20 motivated individuals that included Aaron Corey, Joe Rosalez, Alex Diaz, Anthony Hernandez, Cesar Orellana, Diego Carrizo, Justin Ramsey, Edgar Chavez, Jose Velasquez, Adriana Lopez, Michael Duchetta, Mustafa Ezzedine, Alan Lopez, Justin Jimenez, Emmanuel Diaz, Ryan Yip, Ramon Herman, Felicia Yin, Daniel Marquez, Bernice Santiago, Dr. Sonia Lopez, Isabel Escobar Sanchez. The presentation consists of the following sections: project background, methodology, hydraulic modeling, results, sustainability, conclusion, and references. We begin with the project background. We know that Los Angeles is a water-challenged region that frequently experiences severe drought conditions. Even in normal times, it relies heavily upon imported water supplies to satisfy its water needs. Often the problem of water supply is treated with much greater urgency than the consideration of what happens to the water after we use it. Water treated at the Joint Water Pollution Control Plant in Carson is collected from regional plants, treated, and discharged. Up to 150 million gallons per day are pumped into the sea. More and more water is pumped from local aquifers at a faster rate than can be replenished by rainfall, leaving aquifers at historically low levels. This is concerning because this practice has negative impacts on surface and subsurface conditions. It reduces internal aquifer pressure. It lowers the water table and causes land subsidence. Local aquifers supply 50% of the water used. The remaining 50% is purchased and imported from Northern California and other states. The goal is to replace the regional collection system, which engages in huge wastewater collection, has a huge treatment facility, and produces a huge amount of outfall into the ocean. A decentralized treatment and injection system would collect wastewater, treat it, and inject it locally, recharging the local aquifers. This will increase the local water supply and create a sustainable local water cycle while eventually reducing the need for imported water. Our area of interest was the Los Angeles County town of Pico Rivera, but the larger goal of the project is to encourage the switch to localized water treatment in towns across the county, creating a network of decentralized plants. Some of the impacts of this unsustainable wastewater management system include that it reduces internal aquifer pressure. Lower internal pressure can put the aquifer at risk of briny water incursion, making the water unusable for drinking. It lowers the water table. A lower water table can make the surface soil drier and more hydrophobic, and therefore less able to absorb rainfall to recharge the aquifer naturally. It causes land subsidence. Subsidence is the physical lowering of the land surface above the aquifers due to excessive pumping of the groundwater. This is a widespread problem in the area due to both groundwater pumping and oil extraction. Subsidence is causing major infrastructure damage to roads, bridges, and the municipal water and wastewater systems, all of which are expensive to rebuild and repair. In this image, the water main was ruptured due to subsidence. The resulting leak undermined the road bed and caused the collapse of the road surface. While there is no exact amount forecast for repair costs statewide due to subsidence, estimates are in the billions of dollars. Our Capstone project addresses these unsustainable water management practices by creating an acceptable system for recycling processed wastewater rather than discarding it into the ocean, replenishing groundwater basins which provide 50% of Southern California's total water supply and have seen levels drop to historic lows in recent years, creating a sustainable local water cycle, and steadily reducing the need for purchasing water from other regions except during extreme conditions.
One of the goals of Mayor Eric Garcetti's Green New Deal is to recycle 100% of Los Angeles wastewater by the year 2035. The three overarching goals of our project are in line with this. Goal number 1 is to rejuvenate the water table by the year 2035 to make Los Angeles, the largest city on the West Coast, a sustainable city. Goal number 2 is to reduce the amount of imported water and locally source our water supply. Achieving these goals will sustain local water and infrastructure resources for Los Angeles residents for years to come, and will reduce the need for Los Angeles to import water. Finally, goal number 3 is to use our water resources wisely and educate the community about our project and proposal for recycled water use. This table lists our goals and objectives side by side. To rejuvenate the water table by the year 2035, we plan to replenish groundwater basins with recycled water and by capturing stormwater runoff. We decided a feasible objective to locally source our water supply was to increase our local source of water from 50% to 70% of our total demand. We determined that it is important to earn the public's trust when it comes to proposing new methods of utilizing our resources. And it isn't easy to convince people to consume recycled water, but we agreed that we can start changing opinions by designing an outreach program for local high school students interested in the fields of wastewater treatment. It is important that young students become familiar and are inspired to work on sustainable projects for their communities. Also, this helps raise awareness in their communities on the benefits of recycling water. We just completed the project background. Now we will start with our methodology. To tackle this project effectively, we split the class and assigned the main components to 2 cohorts based on interest and processing capabilities. One cohort was made responsible for modeling the injection of treated water using a 3-dimensional variably saturated subsurface. The other was responsible for designing the treatment facility and injection wells. So to complete this project and create a mind-blowing proposal, we had to complete the following tasks. First, we had to collect all the data available for Los Angeles County. That ranged from soil types, precipitation data, well locations, and much more. Though some data was not readily available online, we had to contact various professionals to obtain additional data. The data was processed so it could be used in our scripts and loaded into our model. After analyzing all the data gathered, we were able to identify and select a site we could conduct a feasible study for. Our second task was to input all our data into our model and obtain the effects of injected treated wastewater onto a shallow water table. But to deliver this proposal on time, our third task had to be completed simultaneously. So the design of the treatment facility was initiated as soon as we started task number 2. The last thing I'd like to mention before moving on is that the way I described this is oversimplified and was much more difficult to complete in practice. We were challenged with processing large quantities of data and conducting research that goes beyond the requirements of our civil engineering curriculum. But using our education, applying our strengths, and coordinating our efforts as a team, we are all proud to report that we were able to successfully complete all the above.
The process by which we chose the location for our model was divided by 3 sections. Borehole data, which gave us information for the types of soils up to 70 feet below the surface. Monitoring wells, which gave us information of the groundwater table at a location. And before we go to the third one, as illustrated on the figure to the right, with both the borehole data and the well locations, we chose to focus on this area of Los Angeles Basin because of the amount of monitoring wells. We will cover more in details later in the presentation for borehole data and wells. Now the third section was geological maps. The maps gave us information of where the aquifers were located and fault lines that would count as our boundaries. With the 3 components together, we chose our site and final domain. To get more in depth with the section geological maps, in the Bulletin 104, we found geological maps and profile views of the Los Angeles Basin. Particularly, we found one where we chose to focus on. The following profile view is the subsurface of our site. The shallow aquifer we have in our site is the Gasper Aquifer. The thickness of the aquifer is about 100 feet. As for the faults, they are below our aquifer, so we didn't have to consider them in our model. As illustrated on the map we created, the final domain that we chose for our model is boxed in the black outline. The area of this domain is approximately 61 kilometers squared.
Project site. We proposed a water treatment facility in Pico Rivera. It is a city located in the southern eastern of Los Angeles County. Pico Rivera's basin is in the northern portion, generally between the Pico Rivera Golf Course and Whittier Boulevard, and in the eastern portion of the basin is bounded by San Gabriel River, and in the western portion by Rio Hondo Channel. However, San Gabriel River was not considered in the model. The reason why is because it is in the cement line, and it does not contribute to the subsurface infiltration. The basin surrounds approximately 864 acres, which is 1.4 square miles in area, and it serves a population of approximately 13,000 to 14,000 individuals. Rivera's land is accompanied with mostly single to multiple family residentials, commercials, and public facilities. We decided to choose this location, which is a great representation of the Southern California, and there are many more residential areas like these. Now, I will be talking about the site selection and tributary. In this project, the collection system hydraulic design will be implemented for our water treatment facility. Most of the information was gathered through Pico sewer line, and we found a network of an existing tributary sewer drainage which would help us define the extent of the capacity for the interceptor. We will later go in depth about the interceptor, pumps, and injection wells. For now, I will be demonstrating where the water treatment facility, pumps, and injection wells will be located. This is where the water treatment facility will be located, southwest from Pico Rivera Golf Course. The injection wells and pumps will be sited as illustrated in the image. Lastly, our water treatment interceptor will be intercepting all of the sanitary sewer lines from the point where Paramount Boulevard and Woodward Boulevard meet. Most of our sewerage flow comes from residentials, that is why we chose this tributary area. Our tributary area is huge and has about 13,000 individuals, which most of them being residentials. And it only has one sanitary sewer drainage line, which makes it effortless to intercept and treat wastewater.
We will now talk about hydrologic modeling. One of our project's main goal is to replenish groundwater basins. In order to reach that goal, hydrologic modeling was used. PowerFlow is a modeling software we use to model surface and subsurface flow. PowerFlow is an open-source numerical model that uses Richard's equation for subsurface flow and applies multiple parameters to create a three-dimensional domain perfect for our project.
To begin the discussion on the domain configuration, I would like for everyone to analyze the figure in the shape of a Rubik's Cube. A typical 3D Rubik's Cube has a configuration 3 by 3 by 3 corresponding to 27 grid blocks. Just like the Rubik's Cube, PowerFlow is a three-dimensional hydrologic model with configurations in the X, Y, and Z direction. The domain configuration used for modeling was 69 by 90 by 25, corresponding to 155,250 grid blocks. The grid block size in the X and Y direction are 328 feet, while the Z direction has a varying depth from top to bottom. The depth at the top of the domain was kept short to capture and represent precipitation that may be introduced into the system. Grid sizing has a substantial effect on the resolution and processing time for modeling. To the benefit of the project, we were able to determine an appropriate resolution needed to represent our data with minimal processing time.
In order to begin the modeling process, we would first need to add our data inputs into the model. Ultimately, our main goal was to try and create an exact representation of groundwater movement, and in order to do so, the key components that were added into the model were precipitation, domain slopes, existing water table, and soil parameters.
Once all the data was input into our domain, we had to spin up the model. Spin up refers to having our model reach realistic hydrologic conditions. or waiting for the water table to stabilize before doing any significant test on our model. If we are to inject water into the ground, it will take years for the water to distribute through the soil before the water table stabilizes. When creating a 3D model, we must first condition our chosen domain and allow the model to simulate existing conditions. Our model domain ran for about 39,048 hours, or approximately 4.5 years, before reaching hydrologic equilibrium.
Precipitation was downloaded hourly for the model, but it was converted to daily for the purpose of this figure. The figure shows the total daily precipitation for the span of 12 years, starting with January 1st, 2007 to December 31st, 2018, which is a total of 4,383 days. The values to the left of the slide are the mean, standard deviation, maximum, and minimum of the annual precipitation.
An important parameter that was considered for our model setup were the slopes in the X and Y direction. The slope can give us information on where the water is going to flow. We know that water flows from high elevation to lower elevations. On the left portion of this slide is a visual representation of the X directional slope of our domain, and on the right is the Y directional slope of our domain. On both figures, we can see that the northern part of our domain is where we have steeper elevations, and this is depicted by the red regions. As we go down south, we notice less steeper regions. From the figures, we can safely conclude that the water would tend to flow to the southern region of our domain, and this will be assured in the upcoming slides when we take a closer look into the results of our hydrologic model.
In order to create the soil profile for the model, the data from 1,210 boreholes was collected from the State of California's Department of Conservation Borehole Database, pictured here on the right. Each borehole captured the lithology of each site at varying depths down to a maximum of 70 feet. A MATLAB script was created to classify the soil composition at each site into 15 soil categories using the soil texture triangle pictured below. Each soil category has 7 different soil parameters associated with it, which include permeability, porosity, hydraulic conductivity, and saturation. Since the boreholes varied in depth, the MATLAB script was also used to fill in the blank spaces in the Z direction using linear interpolation, thus creating a soil value for each of the 25 model layers. Once the data was analyzed with MATLAB, the data was converted into a text file that included the UTM coordinates for each borehole. This file was then imported into ArcGIS and geospatially analyzed. Since each of the boreholes was spaced at different geographic locations, the lithology between each bore site was interpolated using the inverse distance weighted function, thus creating a gridded data set where the changes in soil composition can be observed. The new grid system was then imported into ParFlow, where the effects of the heterogeneous soil structure on the flow of the re-injected water can be observed after spinning up the model.
To effectively model our 3D subsurface configuration, the soil properties of each of the 15 soil types observed within our domain were researched and input to ParFlow. Each soil type was assigned an indicator value which allows for the property variables to be assigned to each soil in the domain. Using the data visualization software Visit, we were able to create 3D images that represent the soil parameters of our domain. The image here shows the variability of permeability within our domain. As seen in the figure, highly permeable soils in red are adjacent to low permeable soils in blue. For ParFlow to model the groundwater flow with this input data, a Gaussian distribution called turning bands is used to streamline the data. Turning bands accounts for the variability in the data by using the averages and standard deviations of the input data so we can be sure that the results from the model accurately represent our test site. Other soil properties that were included in the subsurface configuration and have an effect on how water particles move through the soil in our domain includes porosity, specific storage, and saturated soil properties known as Van Ganukten properties.
So we can have a better presentation of our model, a total of 153 well locations were collected using the WRD GIS application, as shown on the map to the right with the blue circles. However, due to huge data gaps, yearly averages ranging from 1929 to 2019 were performed for each well. Finally, so we could interpolate between the well locations, one value was assigned for each well. After assigning a value to each well, a data file was created where latitude, longitude, and average head values were stored in it. A script was then written in MATLAB for two purposes. A purpose of the script was to convert the latitude and longitude into UTM coordinates, our x and y. The other purpose was to create a gridded file where well locations and their respective water table depth were in the right locations, as shown to the right. The gridded data was then sent to ArcGIS, where we interpolated between the wells using the inverse distance weighted function. The new grid was then used in ParFlow.
In this next section, we will be going over the results. After identifying community needs, acquiring the available soil and well data for an ideal site location, and analyzing that information for hydraulic modeling, the team selected a solution that rethinks wastewater management. In order to mitigate the massive amounts of energy to meet demand and the extensive financial resources required for operation, we selected a decentralized water treatment system to address the collection, treatment, and distribution of the processed water. We will be using the community's existing gravity sewer network to gather wastewater and distribute it under pressure towards one of our 8 package wastewater treatment plants for processing. The package plants consist of 5 tanks, which include an equalization tank to prevent hydraulic overload, capable of holding 33,000 gallons, a sludge holding tank with a capacity of 22,000 gallons, used to store the excess waste activated sludge that is periodically removed by a contract septage hauler once full, and 100,000 gallon aeration tank to activate the sludge and remove organic waste, a chlorine clarifier tank to disinfect and return the activated sludge to the aeration tank, capable of holding 19,000 gallons, and ending with tertiary treatment tanks to further reduce the biological oxygen demand and the suspended solids, with a capacity of 20,000 gallons each. Once the water is treated, the processed water will be conveyed under gravity into wells that inject directly into the underlying aquifer to rejuvenate groundwater levels. A network of existing tributary sewer drainage defines the extent of the capacity for the interceptor sewer in the basin. The basin contains approximately 37 miles of an existing gravity sewer network that are generally sized to 8 inches in diameter. The interceptor sewer collects tributary drainage and, based on the 800,000 gallons per day treatment capacity and projected wastewater production, is designed as a 1.9 mile long, 8-inch diameter steel pressure pipeline, which exceeds the calculated design capacity of 6.2 inches derived by applying the energy equation. This increase in capacity is for unexpected water surcharge due to potential stay-at-home orders from state and federal governments in efforts to mitigate natural disasters or viral pandemics. Specific project details such as maintenance hole spacing, alignment, depth, precise slope, etc. are dependent on the final design requirements, most recent land surveys, soil boring analysis, subsurface utilities, and other detailed substructure investigations to be performed prior to procurement.
As we mentioned earlier, we anticipate a water flow of 100,000 gallons per day to be pumped right into the system, where pressure must be increased because there is an insufficient difference in water levels in gravity flow distribution systems. In other words, the pump will transfer water from point A to point B with pressure to overcome the resistance along its path. In our project, we have a flow from point A to B with an elevation of 33 feet and pipeline that is constructed with a length of 1.9 miles, a diameter of 6 inches, and a slope of 2%.
With the data we have, we were able to find a velocity of fluid in pipe of 6.3 feet per second. Given the material we're dealing with is steel, and by taking in consideration the Hazen equation coefficient of 110, we were able to calculate a total head loss of 373 feet.
The wastewater collected from the community will be treated using A-carbon steel plants and A-carbon steel tertiary filter systems, all performing the same process. The process will begin with sewage water passing through commutators and bar screens in charge of removing, reducing, and cutting any large solids and materials, to then flow into the equalization tank that will act as a buffer and regulate the flow of sewage water to prevent overloading on the hydraulic systems. From the equalization tank, it will enter the aeration tank, which maintains bacteria at specific concentrations so microorganisms can utilize biosolids as a food source and convert untreated sewage into carbon dioxide and clean water. Once the water moves past this step, it enters the clarifier tank, which allows the separation of activated sludge and clean water. When heavy activated sludge settles to the bottom of the tank and is returned to the aeration tank for further treatment, allowing clean water to overflow into the tertiary filter. Only when necessary, the sludge holding tank is used to store excess sludge coming from the clarifier tank, which could either be disposed or returned into the aeration tank for further processing. The last step in this process is passing through the tertiary filter tank, which provides additional removal of suspended solids and allows further reduction of biochemical oxygen demand. Finally, once the wastewater treatment process is finished, water can be conveyed into the injection wells, which will be discussed on the next slide.
Our recharge well is going to be injecting into the unconfined Gasper Aquifer in the Pico Rivera area. The subsurface conditions consist of sandy gravel to a depth of 100 feet where there is then an impermeable layer. The depth to groundwater is on average 45 feet. Given approximately a population of 14,500 people and a usage rate of 50 gallons per person per day on average, we arrived at 750,000 gallons per day. For the sake of simplicity and to give ourselves a buffer zone, we rounded up to 800,000 gallons per day. Luckily, since our aquifer is in a sandy gravel area, the permeability factor is actually quite high at 27.8 feet per day. For our analysis, we used a steady state unconfined aquifer equation to calculate injection rate and the radius of influence, which was found to be 2.02 feet from the center of the injection well. As you might notice, the radius is fairly small at 2.02 feet. However, given that the subsurface material is sandy gravel with a high permeability, it's a reasonable result. In our analysis, there are three scenarios: one injection well injecting at a depth of 70 feet below ground surface, two wells injecting at a depth of 70 feet below ground surface, and two wells injecting at a depth of 90 feet below ground surface. Due to the high permeability of the subsurface material, however, the injection rate was unaffected. Broken down into a per second time rate, the injection rate is 1.234 cubic feet per second.
A well screen is a filter that allows water to exit the pipe from several entry points. The filter can be made from several materials, but in our design, we're taking in consideration only PVC material, since it's light, strong, easy to install, and relatively inexpensive. For our 50 feet well screen with a diameter of 8 inch, a wire width of 0.047 and slot size of 0.035 inch were picked since the properties of the soil we're dealing with is mainly sand. These dimensions were needed to ensure that the water can flow out and the soil particles cannot get in.
From the data collected, slopes, precipitation, existing water table depth, and soil parameters, we were able to model the injection of one well, scenario 1, with a Q value of 800,000 gallons per day drilled at 70 feet. From the figure shown, we simulated the one injection well for an approximate length of 12 total years with the injection well location in the top right corner. From the figure shown, we pulled 4 time steps, day 0, 1461, 2922, and the last day of simulations, 4383, to represent the effect on the groundwater. From the figure and color bar, we can see that the injection well is indeed recharging the groundwater over the course of 12 years. On the next slide, I will elaborate on the increase of water table depth that is shown. The slopes in the model are a driving force on the movement and final destination of the water in the system. As Cesar discussed previously, the steeper regions are located in the northern region and begin to plateau, moving towards the southern region. Because water moves in the direction of least resistance, we can see that the water has traveled to most of the southern region based on the right figure. In addition to the water table figure, we can see that there is a larger water table depth here. This is because the slopes are steeper around this region and have trapped the water over time. In addition to scenario 1, Ramon will discuss and compare the other scenarios that have been modeled.
In addition to the well 1 simulation previously discussed, we also ran an additional 2 more scenarios, which included 2 wells drilled at 70 feet and 2 wells drilled at 90 feet, each with a flow of 400,000 gallons per day. As we can see from the figure shown, well scenario 1, 2, and 3 show that there is no significant change in the water table between the 1 or 2 well configurations. Therefore, the feasible well configuration would be to have only 1 well in the domain.
In addition, the graph displayed is an illustration of the change in specific storage due to the injection wells over time. The graph depicts that the water table is indeed rising over time due to the injection wells, and this is clear as we see an increase in volumetric moisture content as time progresses. As the water table rises, the pore spaces in terms of volume begin to fill up with water. An increase in the water table suggests that the capillary pressure decreases, which would result in an increase in volumetric moisture content. You can also notice that there was not much of a difference in the well scenarios, and this is illustrated on the zoomed in portion of the graph. Ultimately, the graph leads us to conclude that the injection wells are indeed recharging the groundwater aquifer.
Based on the California Environmental Quality Act, we determined that the following categories of environmental impacts that we must address, as well as various solutions to mitigate the impact of the facility. Such factors include the aesthetics, land use, noise, and air quality. The aesthetic impact of the facility is not only limited to the finished product itself, but also the construction. In the process of building this facility, some of the local vegetation will be cleared away. To offset this, it is ideal to use landscaping with plants that are compatible to the area. Doing so will improve the aesthetic of the facility while also reducing the cost of maintenance to the landscape. Due to the proximity of the site to residents and local business, it is important to coordinate with the local jurisdiction on land use. The construction of this facility would require the displacement of pasture from the adjacent golf club, as well as a 1.9 sewer interceptor. Residents in the area as well as local business will be exposed to above average sounds, both during construction and the transportation of waste leaving the facility. To reduce such exposure, it is important to coordinate with the local region to find the time that such noise would be less inconvenient, as well as to reduce the impact on local traffic. Transportation and construction also play a role in the impact on air quality. To reduce the impact of construction, EPA Tier 4 compliant diesel engines will be used for heavy machinery on site. Transportation will require a Class 6 medium single-axle dump truck. To reduce the number of trips while still using a smaller diesel engine, solid waste shall be extracted once a week from an on-site storage unit.
This is a pie chart of our construction cost estimate. The total cost estimate came out to be $28.95 million. The cost is broken down into 9 separate items. Of these, the tangible items are the collection system, the pump station, the treatment plant, and the equalization tank. The bulk of the cost comes from the collection system at $8.5 million.
As you could see, the collection system is the largest piece of the pie, taking up 29%, and the treatment plant is a close second, taking 26% of the cost. The team conducted a cost-benefit analysis. We calculated the operation and maintenance as well as the cost of financing the project, and it came out to $1.6 million annually. We also calculated the cost of the water generated, which turned out to be $600,000 a year. We finally calculated the money saved by not operating the legacy regional water recycling system, and that resulted in an annual savings of $1.4 million. This resulted in a cost savings of $67 per individual living in the community annually.
The next section is sustainability. My colleagues have noted that this project is a sustainable design. So what makes it sustainable? This project is sustainable because it recycles and produces water. By producing water, we are reducing the need for imported water supplies that are very expensive and have a huge environmental footprint in terms of greenhouse gases and impacts to the environment. In reducing the need for imported water, we are reducing impacts to the environment. Such impacts include the reduction of greenhouse gas emissions, since less water will be pumped from distant facilities. In reducing imported water, we are also allowing fisheries and the environment to benefit from the available water conserved at the source. Our design will also increase the drinking water supply. This will be done by recycling our wastewater back into the groundwater table. This will also reduce the dependency on other systems for water. Lastly, the reinjection of water will eliminate subsidence. This will protect our infrastructure and will significantly reduce the cost for damages into the infrastructure. Now, imagine replicating this project thousands of times. The benefits that this project produces could be multiplied, creating a safe living environment for future generations. The implementation of a decentralized water treatment and recharge system will reduce the need for energy-intensive, operations-intensive regional wastewater treatment systems. The production of clean water to inject into the ground increases the internal underground water pressure, reducing subsidence, and in the process protecting local infrastructure. The increase in the aquifer's internal pressure has the added benefit of creating a barrier to seawater encroachment. Lastly, the recycling of wastewater into the ground will reduce the pumping of treated wastewater into the ocean, reducing environmental impacts to aquatic life in the ocean around sewer outfalls.
Now we will move to the conclusion.
From the outset of the project, students were made aware that they would be developing new skills while employing old ones. The modeling team was exposed to the keystone of the project early on, ParFlow. This software was completely foreign to all students and required weeks worth of time outside the classroom to gain proficiency in. Add to the situation that ParFlow operates on Linux, an operating system different from what students were accustomed to, and the result is that students were cramming multiple semesters worth of learning into a single course, while instantaneously putting new knowledge into effect. As is typical with learning new skills, problems arise along the way. In order for the team to properly model groundwater, large amounts of rainfall, borehole, and well data had to be downloaded, and the team quickly found themselves with a backlog of data for almost every hour of every year for 30 years. This was over 1.5 terabytes of data that needed to be downloaded, and would have taken the students months to finish. It was only thanks to the creativity of one student who used a script obtained from nasa.gov to download the data in an efficient manner over the course of 2 weeks. This display of initiative would repeat itself time and time again throughout the project. With the team divided into 2 cohorts, it can be misunderstood that the project as a whole came in 2 very distinct parts, when in reality, both cohorts were codependent on each other and had to develop proper channels of communication. Early on, the cohorts had to clearly define what was required of each other to meet cooperative goals. Combined with the overall complexity of the project and the challenges visited upon the team due to COVID-19, small miscommunications could result in catastrophic setbacks, effectively paralyzing the critical path of one cohort, while the others scrambled to provide the necessary information. Students overcame this communication fissure by developing a joint timeline with established milestones and the contributions required of each group along the way. By the end of the project, students solidified skills learned at university through practical application. Additionally, they developed marketable skills in new software, making them a valuable addition to future employers. Students became proficient at setting team goals, delegating tasks, and allocating group resources to meet joint timelines. More than this, the students were given a chance to solve one of the problems in their community and took it head-on. The team's goal was to rejuvenate the water table and increase the source of local water supply. Through the design of this decentralized wastewater treatment facility, and by using hydrologic modeling, the team was able to achieve this end.
To accomplish our final goal, to educate the community about water reuse, 60 Downey High School students taking AP or Honors Chemistry were invited to tour the Los Angeles County Joint Water Pollution Control Plant in Carson, California on November 22, 2019. The students had a Water 101 presentation from a wastewater treatment engineer on site to discuss water awareness, water sources, the hydrologic cycle, water conservation, and water recycling. The students also learned about potential career opportunities in wastewater management. Hopefully, some will choose to join us at Cal State LA.
I would like to extend our thank you to all the faculty that helped make this project a success. A special thank you to the Metropolitan Water District for sponsoring the project and providing us with a great learning experience. Also, we would like to acknowledge the contribution of the Los Angeles County Sanitation District, the Water Replenishment District, the Department of Water and Resource, and the Stanton Engineering for their technical support on this project. Here we have a picture of when we visited the Joint Water Pollution Control Plant in the city of Carson. Finally, our references.
Thank you everybody for coming to our senior design presentation. I hope you enjoyed the video. I hope you're also able to join us on May 8th from 6 to 8 p.m. for our question and answer session. We're happy to answer any questions about the project. If you would like to join us, you can contact either Dr. Rupa Purasinghe at purasi@exchange.calstatela.edu, or you can contact myself, Sonia Lopez, at slope188@calstatela.edu. Hope to see you all there.